Hello and welcome again to my Physics Online video lecture series. In today's video we're going to be continuing our discussion of nuclear physics and nuclear interactions by looking at mass defect and nuclear binding energy. So in some sense this little short lecture is the basis for how does nuclear power work. Why is it that when we split an atom we get energy that we can use to boil water to essentially spin a turbine and generate electricity? For that matter, why is it that when we fuse two atoms together to make a bigger atom, a bigger nucleus, why do we get energy from doing that in some cases as well? So today's basically video is going to be going into how much energy is actually stored in a nucleus in some sense. The, in some ways, important equation, and I will put this under recall, is Einstein's equation that converts between mass and energy, which is one of the more well-known equations in physics today. That is the E equals mc squared equation. Alright, so that basically means that if you know the mass of a particle at rest, then you should also know what its rest energy is. If that particle were to be somehow annihilated, how much energy could it release just by being a particle? The second thing we might want to recall is that we also use these special units, the EV, to represent energy, where 1 EV is defined as the energy being gained by an elementary charge being accelerated across a 1 volt potential difference. So let's work a little example with these information. What's the rest energy of a proton? How much rest energy does a proton have? Well, we know that the mass of a proton is approximately this number. There are of course more digits. We can plug in to the Einstein equation, which gives us E is mp times c squared, and so we multiply this mass times c squared. That gets us an energy in joules. Now we can of course convert that into EV by recalling that the elementary charge E is about 1.602176 times 10 to the minus 19 coulombs, and so that means that 1 EV is approximately 1.602176 times 10 to the minus 19 joules, because 1 coulomb through 1 volt is 1 joule. So basically we would need to then multiply this by essentially like 1.60 1 EV per 1.602176 times 10 to the minus 19 joules, and that would get us our mass, our rest energy, in these EV units. So for a proton, this ends up being about 9.3822179 times 10 to the 8 EV. Put differently, that also means that the mass of a proton is approximately 938.2179 mega electron volts per c squared in our same unit system. Alright, so today we have a few things to do that are new. One is to introduce a new unit. So new unit is called the atomic mass unit. Now the way the atomic mass unit is defined is that it is 1/12 of the mass of a 12 nucleon carbon atom. Now the atomic mass unit has units itself, of Daltons. Now this unit is used a lot in chemistry. It's used sometimes in nuclear physics. Basically what it does is it gives us a simpler way of comparing masses of things. So in some sense we can just compare the masses of nuclei to the mass of, well, other nuclei. So a carbon-12 nucleus actually has a mass of just under 12 daltons. Why just under? Because we also have electrons in that carbon atom, and that's part of the total mass. But we're very close now. We can say in some sense that one nucleon has a mass of very nearly 1 U. Now the interesting thing is that when we look at actual masses of nuclei, what we find out is that it doesn't necessarily follow that more nuclei linearly increases the mass of the nucleus. It's close to a linear relationship, very, very close. Part of why that's not true is because a neutron and a proton both are nuclei. You can find both of them in a typical nucleus, but you can have different ratios of the two to get the same total atomic number. So recall that you have this thing called an atomic mass number A, which is given by the number of protons in the nucleus and the number of neutrons in that same nucleus. And so if you have A equals, let's say, 10, that could be formed by having, say, 6 protons and 4 neutrons. It could be having 5 of each. It could be having 4 protons and 6 neutrons. All of those should give you different masses. So in and of itself, just knowing the atomic mass number doesn't necessarily mean you're going to know the total mass. And in fact, it's actually in some ways worse than even that, because as it turns out, depending on how many protons and how many neutrons you also have a quantity called mass defect. So mass defect, and usually is represented as delta M. This is the difference in mass that you would get for a nucleus, a given nucleus, by having the actual mass of the nucleus and then by adding up all the protons and adding up all the neutrons and finding their masses. So in some sense, the equation for this is delta M is equal to Z, that's the number of protons, times mass of protons, plus N times mass of neutrons, minus M total, or M nucleus. Maybe we could call that, we'll call it M total so we're not confusing it with M neutron. So put differently, if you actually were to go and measure the masses of various nuclei, you'd find that that mass somehow falls short of the mass that you should expect if you were to multiply the constituent components and their masses together. Now this mass defect has to be made up somehow. Energy has to be conserved. If I put two, let's say I put a proton and a neutron together, this forms the nucleus of a deuteron, a hydrogen with a proton neutron. It's called a deuterium atom. So it's a deuterium nucleus. There ends up being some mass defect. And so what does that mass defect represent? Well, for energy to be conserved, this means that we expect there to be a sort of delta E present. And so this delta E is what's called the binding energy. And that binding energy, delta E, for a given nucleus is given by delta E is equal to delta M, that is the mass defect, times c squared. So if I know what my mass defect is, then I can from there determine what the binding energy is. Now, because I've introduced this unit of the atomic mass unit, and we now are talking about binding energies, it's kind of worth noting that the atomic mass unit is equivalent to 931.5 roughly mega electron volts per c squared. So if I have a mass defect of 1 atomic mass unit somehow in my nucleus, they're not usually that high, but if I have a mass defect of 1 atomic mass unit, then that means that I have a binding energy of 931.5 MeV over c squared times c squared. And so that would mean that my binding energy in this case is 931.5 mega electron volts. Okay, and so that's how we basically get to what the binding energy is. All right, as an example, let's consider the common nucleus of helium. The common nucleus of helium is A equals 4, Z equals 2 helium. That means atomic mass number 4, 2 protons, ergo 2 neutrons. So if I'm going to do this, I need to know what is the actual mass of the helium. And that's this number right here. So this right here would represent what I've labeled as M total. So to get the mass defect, I basically need to use delta M, that's our mass defect, so that would be delta M, binding energy delta E. Delta M is Z times mass of proton plus N times mass of neutron minus M total. Okay, so coming back up here, this right here is saying A equals 4. This right here is saying Z equals 2. And we know that A equals Z plus N, which implies that N is Z minus, A minus Z, or 4 minus 2, or 2. So coming down here, my mass defect delta M is equal to 2 times mass of a proton. Now mass of a proton, we could either convert the unit, the U, over into kilograms or EV over c squared, or we can convert these to U's. The mass of a proton in U's we kind of found, or could find earlier from the example that I worked. It comes out to about 1.007276 U. And then for the neutrons part, we have 1.008665 atomic mass unit. And then from that, we're taking away 4.002603 atomic mass unit. So that gets us a total of 0.029279 U or Daltons for mass. Now to get the binding energy from this mass defect, then we can multiply by this 931.5 approximately MeV over c squared dot U, or MeV squared per U. And so that gets us a delta E of approximately 27.27 MeV. So that is your binding energy for that nucleus. And essentially, in some sense, when you do nuclear reactions, which is a separate video, when you either have a nuclear decay, when you have a fission event, when you have a fusion event, the energy that you pick up comes from differences in binding energies, maybe per unit particle if you'd like, times the number of particles present. So if I have 2 deuteriums and I've got some binding energy for each of those, and I add those binding energies together and I smash them together and get a helium with a 4 and a 2, and I have a different binding energy than the sum of those previous 2 binding energies, that difference is the amount of energy that we would expect to either be required or in some cases be released by that reaction. So to wrap things up, I should maybe say, like, where should you go to get the total mass of a given nucleon? And the answer is, as a student in an undergrad class, you're pretty much going to go look these things up, usually compiled from data that somebody else has taken. Some textbooks, though not all, have a nice set of tables. For example, this is the table that Sears and Zemansky's physics provides, and it even tells you where the source is. So you could maybe go to this paper directly if you'd like and try to look at their data. This is only really looking at relatively light elements. You'll notice that the atomic number is only up to 8, which is oxygen. This isn't looking at like uranium or plutonium or any of the other heavy and radioactive elements. But it does give you your atomic number, your neutron number, therefore your mass number, which is the sum of these two, and your actual atomic mass out to several digits of precision. So that's a good start. And then for what it's worth, I've compiled a sort of table of what are the masses in each of these 3 units for the proton, the neutron, and the electron that you can use if you want to do some more problems of this sort. So that's all for today's video. Hopefully you've learned something for it, and as always, thanks for watching.